Okay, so now we'll move on to matrices. Okay, so let's first import numpy as np, and run it. Okay, so a matrix is also a numpy array. So let's create our first matrix m equal to np dot array of. So the first bracket I'm opening, and then this is going to be a list of lists that I'm passing to np dot array. Okay, so this is 1 2 3. That's the first row of the matrix. 4 5 6, and then 7 8 9. Okay, now if I run this, notice that I have a numpy array. Okay, this is also a numpy array, but this is a matrix. Okay, we call this a numpy array of dimension 2. So these are two dimensional numpy arrays because you have rows and columns. Okay, so we'll get back to that right at the end. Dimension. For now we'll start looking at simple operations, mathematical operations that we can do when we have a pair of matrices, and how we can translate them into numpy. Okay, so we have a, which is given to be 1 2 3 4. That's the first matrix, and you have another matrix that is 5 6 7 8. Okay, now what we need to do is add these two matrices. So how do we add two matrices? As simple as a plus b. Okay, so this will, remember that matrix addition is component wise, so we end up with a plus b. Once again, the theme that I have been stressing on since the first notebook is the way mathematical expressions are translated into numpy. Okay, and the similarity that you can see between the mathematical expressions and their numpy counterparts. Okay, so that is what I want you to focus on. Next operation is scaling a matrix. So how do you scale a matrix? You have np dot array. First, let's create the matrix. So 1 2 3 4 5 6 7 8 9, and we want 3 times m. So what do? We just multiply this by 3. We use the star symbol here. Okay, so that's scaling a matrix, as simple as that. Now we look at element wise multiplication of two matrices. Note that this is not matrix multiplication but element wise product. Just as we had the Hadamard product for two vectors, here we have the element wise product of two matrices. How do we go about doing this? First, let's create these two matrices. It's 1 2 3 4, and b is np dot array of, inside you pass this nested list 5 6 7 8. Okay, and what is c? C is a star b. Okay, and if you visualize or if you run this, you will see that c is the element wise product of these two matrices. Okay, so a very important point here, this is not matrix multiplication. I'm once again stressing this point. This is element wise multiplication of two matrices. Okay, so that takes us to element wise functions of matrices. Few more of these functions. So what's the first one? We have the absolute value. Sometimes you might have to take the absolute values of all the elements of a matrix. How do we do that? So let's first initialize the matrix. Okay, minus 1 2 and minus 3 minus 4. The absolute value is nothing but np dot apps of a. Okay, what that will do is that will take the absolute value of each element of the matrix. Okay, so this np dot apps will be applied element wise. You could also do it for a scalar, by the way. So np dot apps of minus 4, that would give you 4, and you could also do it for a vector. So np dot array of 1 2 minus 3 4 minus 5 would give you 1 2 3 4 5. Okay, we didn't look at the np dot apps earlier, but we are just introducing it here. And I just wanted you to understand that this is applicable for vectors also. It's applicable for numpy arrays in general. Therefore, it's also true for one dimensional numpy arrays, which are what we have been calling vectors so far. So next example of an element wise operation is squaring. Okay, so what is a is np dot array of 1 comma np dot sqrt of 2, square root of 2. So this is a list, right? So this is the first row of the matrix. So np dot square root of 2, and then you have np dot square root of 3 comma 2. So if you know 2a square, or you call it b, right? So b is a square. B is nothing but 1 2 3 4. Once again, please make a note of this. This is not a matrix multiplication a. This is element wise squaring, or You are squaring every component or every entry in the matrix A. All right, that is something you have to keep in mind. Next, we come to one of the most important operations, which is the transpose of a matrix. So how do you find the transpose of a matrix? Let's start with defining the matrix that we are given: 1 2 3 4 5 6. It's a 2 cross 3 matrix. Okay, and how do you find the transpose? M transpose, the rows and columns have to swap. So how can we do this? This is m dot transpose of. This is one way of doing it. Alternatively, what you could do is you could do np.transpose, a method of the NumPy library. That will also work, but what we will stick with is this nice notation m.t. Okay, so all that you need to do is matrix dot capital T. Okay, remember it's not small t, that will throw an error. It's m dot capital T. Okay, that's the transpose. Now, given that this notation is very close to the mathematical notation of transpose, m transpose, there it's a superscript, here it's m dot t. So we'll stick to this particular form while taking the transpose. Okay, so that brings us to the idea of shape and dimension of a matrix. Recall that NumPy arrays of single dimension of one dimension, where we were treating them as vectors. So what about matrices? So start with defining this matrix: 1 2 3 4 5 6. Now m dot shape. What is m dot shape? It's 2 cross 3. Okay, so shape of a matrix is going to be 2 cross 3 of this matrix is going to be 2 cross 3. In general, if there are m rows and n columns, the shape of that matrix will be m cross n. So it will be represented as a tuple m comma n. So notice that the type of m dot shape is a tuple. So it's a tuple. Now that is the shape. What about the dimension? So what we usually call the dimension of vectors and the space in which these matrices lie, that is different. So what we are interested in here is the NumPy dimension in dim. So that is 2. Okay, so there is a row and a column, if you can think about it that way. So there is a row and a column, there are 2 dimensions involved. So this is a NumPy array of dimension 2. So we are going to represent matrices as NumPy arrays of dimension 2. Recall that we represented vectors as NumPy arrays of dimension 1. All right, so that ends the discussion on shapes and dimensions of matrices. So once we have discussed this, we can now turn back and look at vectors as matrices. This is something that we do even in mathematics, right? So we can now talk about row vectors and column vectors. Okay, so let's see. Let's take a vector x. Okay, so what would we have usually done? This would be a vector, right? 1 2 3. Now, how can we represent this as a row vector or a column vector? Okay, so if I want to represent this as a row vector, what should its dimension be, or sorry, what should its shape be? So it should be 1 cross something, right? In this case 1 cross 3. So I can represent it in the following manner, right? So this is 1 cross 3. Okay, so this is 1 cross 3. This is a row vector. How would I represent this as a column vector? It should have shape 3 cross 1, right, as a column vector. So how is that going to look like? So it will be a column. So it will be 1, that will be the first row. The second row you'll have 2, the third row you'll have 3. And if you look at x dot shape, that's 3 cross 1. So what is x in this case? You can see that this is a row vector. You can see that this is a column vector. Okay, now you can't explicitly write things down like this always. So if you have a one dimensional NumPy array, right, such as x equal to np dot array of 1 2 3, you need a mechanism to convert this into a row vector and column vector at will. Okay, so you, with a simpler process, okay, or with a simpler operation, you can't write it down. You can't manually keep adding brackets or parentheses around your elements, right? That's not possible. So how do you do it programmatically? So there is a method that uses what is called a new axis. Okay, so I'll leave it to you to refer to this in the web page. What I'll do is probably a simpler one called the reshape operation. So what does that do? So first let's take the one dimensional numpy array. Okay, this is x. Now what we can do is we can reshape x, meaning it is having a certain shape. We can now reshape it. How do we want to reshape it? We want to change its shape. We want to turn this into a row vector which is 1 cross 3, right? So I want to reshape it in this manner. Okay, so I'm going to rechristen this x. And what is the shape of x now? 1 cross 3. So what is x? It's the row vector. Okay, now I can likewise do this. So this is 1 2 3, and x equal to x dot reshape. Instead of having it as a 1 cross 3 vector, a row vector, I want to turn it into a column vector. So that would be 3 cross 1. So if I now visualize this, it will be 1 2 3, and the shape of x would be 3 comma 1. Okay, so that's how we are going to change 1D arrays into 2D arrays in the case of vector to row vector, vector to column vector conversion. Okay, so that's about row and column vectors. Now we'll come to matrix multiplication, right? So there are actually quite a few things here. There are 4 different ways of looking at it. So first we'll look at matrix product, matrix multiplication as we call it. So let's start by defining these matrices. So we have 1 2 3 and 4 5 6. First matrix A, and B is 6 7 8 9 and 10 11. Okay, so how do we multiply them? This is matrix multiplication. Look, so remember that. First, let's see if they are compatible for multiplication. So shape of A is the shape of B is as follows. So this is 2 cross 3, 3 cross 2. So 3 here, 3 here. Therefore, they are compatible for matrix multiplication. We can go ahead and do it, perform it. So A into B will not work because this is, as I already mentioned, this is element wise product, right? So if you actually try to do this, you'll get an error. So operands could not be broadcast together with shapes. So we'll come back to what this broadcast means later. But for now, it just means that you can't multiply these two element wise. Okay, that simply is not going to work. So what is that we are looking for? Matrix product, right? So therefore, this we introduce this notation called at. Okay, now if you run it, you see that it's 50. It's the product of A and B. You can do it, verify it by hand, and see that it turns out to be this one. So where have we seen this before? Remember that we have seen this at symbol, at operator earlier when we were trying to compute the dot product between two vectors. Okay, miraculously the same symbol or same operator works when we are trying to multiply two matrices, and it gives us the matrix product. We'll see that this is not some one-off occurrence, and this idea of using at for different kinds of products will keep recurring. Okay, so now we have a matrix and a column vector. So if you have A and you have X, AX, how do we multiply these two? So we'll start with np.array of 1, 2, 3, 4, 5, 6, and 7, 8, 9. That's the matrix. And then you have the vector, which I'm going to treat as a single one-dimensional numpy array, 6, 7, 8. So how do we multiply these two to get C? Turns out that you can use the same operator at, okay, without any changes. So NumPy kind of figures out that on the right you have a vector. So internally what it will do is, this is of A is of shape 3 cross 3, right? And X is of shape 3 comma. So what it will do is internally it will turn X into a column vector so that you have shapes 3 cross 3 and 3 cross 1. Okay, now they are compatible for matrix multiplication. It will multiply them. The result will be a 3 cross 1 numpy array, and then it will drop the dimension, the second dimension, right? Or this axis it will drop, and then it will return a numpy array, single dimensional numpy array of shape 3 comma. Okay, so that's internally what's going to happen. We don't need to, so we could have alternatively, what we could have done is we could have started this way. So let's say we have X like this, so we could have reshaped X. Okay, how do we reshape it? As a column vector, so 3 cross 1. So now we have a matrix 3 cross 3 here, 3 cross 1. So that would have given us this vector. What is the shape of this vector? If you notice, this is 3 cross 1. And what did what was the output? 44, 107, 170, right? And then what you can do is you can reshape it back. Okay, you can reshape it back to 3 comma, so that will end up giving you the previous result, right? But then numpy takes care of all of this. You don't need to explicitly reshape it to 3 cross 1 and then reshape it back to 3 comma. You can leave it as a at x. Okay, and numpy will figure out that you are multiplying a matrix and a vector, right? A column vector. So something similar happens for the row vector. Once again, let's start with a row vector matrix product. So this is 1 2 3 4 5 6 7 8 9, and then you have x as np dot array of 6 7 8. Okay, now what do we need to do? We need to do x transpose a. Now recall that for a single dimensional numpy array, x transpose and x are the same. Now what happens is c, if you want to find out c, it is just x at a. Of course, for clarity you could write this as x transpose a, but it doesn't mean anything, right? Or it doesn't mean anything new. It's just the same x. So we could as well stick to x at a, and then it will give you the row vector matrix product. Okay, so notice that the result is a row vector, but then since we are representing vectors as numpy arrays, this is just a array of dimension 1. Okay, so that is internally. How does numpy do it? As I mentioned earlier in the previous case, x will be converted to a matrix of shape 1 cross 3, and then 1 cross 3 and 3 cross 3 matrix multiplication will happen. The result will be a 1 cross 3 matrix or a row vector, and then you will drop the first dimension, the first axis, so to speak, giving you a single dimensional numpy array of shape 3 comma. Okay, so that's what happens. So now we come to the dot product. This we have already seen before, but then you will notice that the unity in this notation is retained. So the dot product is just x at y. Okay, so notice that for the dot product for matrix vector vector matrix 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 product, for all of them, all that you had to do was make sure you had two numpy arrays on the left, one on the left, one on the right. So two numpy arrays, one on the left, one on the right. These are the two operands, and in between they are joined by this at operator. Okay, and the result is whatever product makes sense, right? In this case it's matrix matrix, in this case it's matrix vector, in this case it's vector matrix, and in this case it's vector vector. It's the dot product. Okay, such a powerful operation, and you can see the elegance and the simplicity of the whole thing. All right, so finally there is also one more product which is called the outer product. So here what you can do is you can, so the outer product, if you remember, those who have studied machine learning techniques would have come across this in PCA, where you had to compute the covariance matrix xx trans sigma xa xa transpose. So yeah, so what is the outer product? Now there is a method called outer that will give you the outer product between two vectors. So this is np dot outer, this is xy transpose. You could do it this way, or what you could do is, so you can't do x at y because that's the dot product. So that is something you should already know. What we need is a matrix as output, right? So that's the outer product. Now if you want x x at y to, so x at y, as I said, will not give you the outer product, but if you want to somehow still use the at operator, what you can do is you can reshape x as a column vector and y as a row vector. So if you reshape x as a column vector, in this case 3 cross 1, and y as a row vector 1 cross 3, and then if you multiply them, then you will get the outer product. Okay, so here this explicit reshaping is necessary if you want to make use of the at operator. Okay, so that's about it. Now let's look at some special matrices. That's about matrix multiplication, and now let's look at some special matrices. So you have a matrix of zeros. How do we get hold of this? Remember that we did this for vectors, right? A vector of zeros. A similar notation comes handy here. So we want 2 cross 4 matrix of zeros. So it's np dot zeros of the tuple 2 comma 4. Okay. What about ones? M equal to np dot ones tuple, this in this case it's 3 comma 2. That's matrix of ones. Okay. And now the identity matrix. So I equal to np dot I. It's nicely termed method name. So np dot I of 3 will give you a matrix of size 3 cross 3. That's the identity matrix, right, of size 3 cross 3. Another useful matrix is the diagonal matrix. So np dot diag, you just need to pass the list of entries on the main diagonal. In this case 1 2 3 4, and that will give you the diagonal matrix. Okay, that brings us to slicing, indexing in arrays. It's a very important concept, but thankfully it is reminiscent of slicing and indexing in Python lists, so it's not going to be too hard. So let's start with the following matrix, which is a 2D numpy array, and see how we can get hold of the element 5, okay, using indexing. So how can we do this? Notice that this is nothing but the first row in terms of zero indexing. So I'm going to use zero indexing as in Python. Therefore, when I say first row, it's it's actually the second row. Okay, so I hope you get this. So this is the zeroth row, first row, second row. So first row m of 1. Okay, what will the first row give me? It will give me 4 2 5. All right, what do I need in the first row? I need the second element. So zeroth element is 4, first element is 2, second element is 5. So m of 1 2 will give me the entry 5 that I'm looking for. Alternatively, what you can also do is you could do it in the following way: m of first row. So this is row comma column, right? So this is first row, zeroth index, zero indexing convention, and comma second column, zeroth column, first column, second column. That will also give us 5. Okay, so this comma is maybe new to you, but you must get used to it, right? You could either do it this way. This is like a Python list of lists convention, right? First list, you index into the first list, and then you access the element in that internal list, right? That is the Python way of looking at it. This is the more numpy way of looking at it, where you are a 2D numpy area, so there are two dimensions. So this is like axis 1, axis 2, or axis 0 and axis 1, and you're accessing a particular element. Okay, now, what about a row slice? If you want to extract the third row, in this case, I have defined this as the third row. So, in our zero indexing convention, this will be zero second row, right? 0 1 2. So how do you do that? So this is an numpy dot array of, so this is a big matrix or a long lanky one. So let me write it down: 7 8 9 10. So what do I want? I want m of 2, right? So 0 1 2. So that will give me the second row using zero indexing, right? So m of 2. So sometimes what we do is we add 2, okay, that is in the zeroth axis or axis 1, depending on how you look at it. You are accessing of the second entry in that particular axis, and you want to extract all entries corresponding to that. Okay, so therefore we add a colon, right? So this will become, this perhaps is confusing at this stage, because why do we need this colon really? It worked even without that, right? So, but what we are, this is more of a Python notation, right, where it's a list of lists, and then you only need the outer list here, right? Or all. Okay, how do I put it? So there is the outer list. The outer list is made up of 5 inner lists, and you want the second inner list. Okay, all the elements in the second inner list. You don't want, if you had wanted a particular element, you would have maybe indexed again, but you just want all the elements in the second inner list, so you just leave it at that. This is more of a Python notation. If you want to do it in NumPy, what you would do is, I want in my first dimension, which is the row dimension, right? So it's like top to bottom. I want the second entry, which is 0 1 2. Okay, but then do I want anything particular in this, in the column region, or along that particular row, or along the second dimension or the second axis? Am I looking at a particular element? No, I'm looking at all elements in that axis. Therefore, it's the colon stands for that. Extract all elements from the second axis. Okay, this will become clear when we do the column slice. So let's take a look at this matrix. So this is 1, 2, 3, 4, 5, 6, and 7, 8, 9. So what we want is the second column. So in this case, 0, 1. So second column, but I'm let's follow zero indexing again. So you want the first column. So zeroth column, first column. So I want to extract the column having entries 2, 5, 8. How do I do this? Right? So if you were using the Python convention of list, this whole list of lists, you might have to write a for loop. But thankfully, you don't need to do that in NumPy. So what are we trying to do? Remember that there is a comma that separates the two axes or the two dimensions. I want to extract the second column. So, or rather, using zero indexing, column 1. Okay, the first column. So that is fixed at 1. And then I want all elements in that column. Therefore, I use a column. Okay, so I hope you get this. This is slightly tricky if you're seeing this for the first time. So I want everything from the first column. If I had wanted a particular element, I would have said if I want to extract 2, I would have said 0 comma 1. But then I don't want just 2, I want everything. Therefore use the column. Okay, so that is the column slice. Submatrix slice is a slightly advanced notion of the whole thing. So it's you have this big matrix 4 cross 4, 12, 13, 14, 15, 16. Okay, now what do we want? We want to start from index 1 in the along the rows. We want to start from index 1, end at 2. Therefore I have to go till 3, right? So 0, 1, 2, I have to go till 3 so that I end with 2. So 1 to 3, that's on the first axis or the first dimension or the row dimension along the rows. Along the columns, I want to start at 0, 1, 2, right? I want to start at 2 and I want to just keep on going because there are, I want to extract all the columns after that, so I can just leave it as it is. And this will give me that submatrix slice. Okay, as simple as that. So this is the usual slicing that we are doing in Python, but then we are doing it along each axis of the NumPy array. That's the advantage that we have here. Okay, so that brings us to, I think, the last section of this collab where we are looking at this notebook where we are going to look at some of the operations that you do in linear algebra. How can we translate that into NumPy? Okay, so let's start with this matrix. I'm not going to write the whole thing again, so I'm going to copy this. So that is the matrix. And what do we want? We want the rank. So the module that's going to help us here is the linear algebra module, linalg. So the method that we have at our disposal is matrix underscore rank. So in this case, the rank of the matrix is 2. Okay, so that's the rank. What about the determinant? So this is the matrix. Let me know. I have to write down the matrix in full. So 0, 1, minus 1, and 1, 0, 2. So once again, np.linalg.det of m will give you the determinant, right? So this is, in this case, the determinant is 1. What about the inverse? When the matrix is invertible, so you start by defining the matrix. So it's 3 comma minus 4 and 4 comma 3. So in this case, it's invertible. You can see the 3 square plus 16, right? That's not 0. So np.linalg.inverse of m, that will give you the inverse. Okay, so what happens if you pass a singular matrix, a matrix which is not invertible? So one such example is, say, 3 comma 3 comma 3 comma 3, right? This is not invertible. So how do we verify that? You can look at the rank. So the matrix underscore rank of this, the rank of this matrix is 1, not full rank as you expect. So it's 1. It should not be invertible. But if you persist in finding the inverse, what will happen? It will throw an error. So it's a linear algebra error, right? Linalg error, singular matrix. Okay. So you have to be careful while you are computing inverses. So what about the pseudo inverse? Right, the pseudo inverse for matrix we can compute now. So pseudo inverse, remember, exists for every matrix, not just for square matrices. So it's called the Moore-Penrose inverse. So this is just np.linalg dot p of m. Okay, pseudo inverse comes in handy in many cases, right? So this is the pseudo inverse of m. Okay, now we come to solving a system of linear equations. So you have a theta equal to b, and you want to find theta where you are given the coefficient matrix a and the vector on the right hand side b. So how do you estimate theta? Okay, so if it's invertible, of course, if a is invertible, what you could do is you could find a inverse and then multiply that b. That's possible, but then numpy provides a method to do this. So let's see how that works. So it's 2 3 minus 4. I'm first writing down the coefficient matrix 1 1 minus 1, and then 2 1 1, let's say, and b is np dot array of minus 4 0 7, right? So that's the vector. And then what is theta? Theta is np dot solve a comma b. Okay, I'm sorry, this is not np dot solve, it's np dot linalg, right? So it's inside, sitting inside linear algebra. So you pass the coefficient matrix in the vector, and the result is 1 2 3. Okay, so that's nice. Okay, so if the matrix A is singular, okay, or if it's not a square matrix, then this is going to return an error. Okay, so now let's move on to the least square solution. Sometimes a theta equal to b may not be solvable, okay, or may not have a unique solution. So what do we do in such situation, especially in the case where a theta equal to b does not have a solution? What do? We look for an approximate solution, and that is given to us using the least squares method. Okay, so let's see how we can extract the least square solution. The coefficient matrix again is 1 1 minus 1, 2 2 minus 2, and b is np dot array of minus 4 0 and 0.1. Okay, so let's try to solve this np.linalg.solve a comma b and see what we get. We get a linear algebra error. Okay, it's a singular matrix. In fact, we can verify that it's indeed singular by looking at np.linalg.matrix rank of a, and the matrix rank is 2. It's not full rank, therefore it's not invertible. You can't use the solve method. So what do you do in such situations? You can use np.linalg.lstsq. So this is the least square system. You pass a, you pass b, and this returns a bunch of things. In fact, it returns the rank of a matrix and several and two and something else also. But what we are interested, let's okay, first let me first run it so that you get a sense of what I'm talking about. So it returns a tuple, right? So what is the type of this object that it returns? It returns a tuple. And what is the tuple? How many elements does it have? What that tuple? So let's look at length of this tuple. It returns four things. Okay, four objects. And what we are interested in is the solution, the least square solution. That's the first entry, okay, or the zeroth entry. That's what we care about. Okay, let's call that theta. So this is theta. Okay, so let's also study a theta. Remember that the whole idea of least square solution geometrically is that a theta should be approximately equal to b, meaning you must find a theta such that a theta gets as close to b as possible. Okay, if a theta equal to b is a consistent system, then you will find an exact theta. If not, you must be able to get as close to b as possible. Okay, that's the whole premise. So let's first compute a theta and see how close it is to b. So this is a theta is minus 0.4, 0.04, 0.08. Remember that you want it to be close to b. See, what is b? It is minus 4, 0.1. So notice that these two are quite close. Okay, now that's what we expect. All right, so then we come to finding the eigenvalues and eigenvectors, another important operation that we might have to perform. So you have the matrix 1 0 minus 3, this is 0 5 2 minus 3 2 8. So in this case this is a symmetric matrix, and when you have a symmetric matrix, there is a method in the linalg module called h. H stands for Hermitian, or Hermitian, recall, is the complex analog of symmetric matrices. So np.linalg.h will give you two objects. It will give you the eigenvalues and eigenvectors. So I'm going to call them eigval and eigvec. Okay, so what are the eigenvalues? Let's first look at the eigenvalues. Remember that they'll all be real because you have a symmetric matrix. So eigenvalues will be real. So these are the eigenvalues. They are arranged in ascending order, and the corresponding eigenvectors live in eigvec. So it's represented as a 3 cross 3 matrix. So how are they represented? So for eigval 0, the first eigenvalue, the first column of this matrix will be the eigenvector, corresponding eigenvector. Okay, so eigvec. Sorry, this is eigvec. So what does it mean? So for the eigenvalue minus 0.209, the corresponding eigenvector is the zeroth column of the eigvec matrix that is returned. Okay. Likewise for the first eigenvalue or in terms of zero indexing, right? This is the corresponding eigenvector. So on and so forth. So remember that this is a column slice. So I'm slicing the first column. Okay. So that's eigenvalues and eigenvectors for symmetric matrices. Now for in general, the eigenvalues may not be real. Okay, so but then you still have an eigenvalue method. So np.linalg just take right of m. So that will give you eigenvalues and eigenvectors. So equal eigvec. So you know, notice what the equals are. In this case they are complex eigenvalues. Okay, so notice that ordering doesn't make sense anymore. So in the case of symmetric matrices, you had real eigenvalues, so you could order them, and the order was ascending order. Okay. Okay, so the final part is SVD, right? So this is a very important matrix factorization technique, right? So let's first write down the matrix. This is 131 and 242, right? So this is M. So now let's compute the SVD of M. Remember that SVD of M is of the form U sigma V transpose, where U is the matrix containing the left singular vectors. Each column is a left singular vector. The sigma is the diagonalish matrix that has the singular values on the main diagonal arranged in descending order, and then V is the matrix of right singular vectors. Okay. So how do we compute the SVD of M? So we have np.linalg.svd of M. Okay. So that will return three things. So it will return U sigma and V transpose. So we'll have U sigma and V transpose. That's how I'm going to express it. So what are these three? So U is whatever I just mentioned, right? It's a matrix containing the left singular vector. So it's a 2D array. Sigma is actually what we want is a diagonal matrix, but then since we are only interested in the singular values, we are going to get the singular values. So let's first look at sigma. It's a vector. Okay, so in this case, there are two singular values, two non-zero singular values, and that's what we have. So it's a 2 cross 3 matrix, right? So M is a 2 cross 3 matrix, so you can have at most two singular values. So in general, if you have an M cross N matrix, you'll have at most minimum of M comma N singular values, right? So that's what we have here. We have two singular values, and it's a 1D array. Okay, and you can easily recover the sigma diagonal like or diagonalish sigma matrix from here. And what are U and V? U and V are orthogonal matrices, meaning U transpose and U transpose URI. So let's see if that is the case. So first compute U and U transpose. Okay, so that's what we get. It's I, and let's say V transpose. So it's VT, because V transpose, it doesn't matter whichever way you do, you have to get the identity, right? So you can see that the off diagonal elements are as good as zero, so they are like extremely small numbers. Okay, so this is the identity. Now what we'll do is we'll quickly see if SVD computation is correct. So before that, let's look at the shapes of these three matrices. So we use 2 cross 2, V is 3 cross 3, okay, sorry, V transpose, and sigma is a numpy, a 1D numpy array, right, has having a singular value. So if you want to reconstruct M using this, what should you do? You should multiply the 3 U sigma V transpose. However, the shapes are not going to match, right? So this is 2 cross 2. This is not even a matrix, right? It's a numpy, single dimension numpy array. It's a vector, and this is a 3 cross 3 matrix, right? So what we need is, we'll retain you. This is 2 cross 2, and let's turn this into a diagonal matrix, right? So this is np dot diag sigma. So now let's do this step by step. So u is 2 cross 2, and then np dot diag of sigma, singular values, that is 2 cross 2, right? So you have u sigma, and you need v transpose. So note that this is anyway having only shape 2 cross 2, right? So you don't need 3 cross 3 there. It's enough if you retain the first 2 rows of v, okay? So v is, I'm just going to retain the first 2 rows of v transpose, not v but v transpose, sorry. So it's enough if you retain the first 2 rows of v transpose. It's the same as saying it's enough if you retain the first 2 columns of v, but then what SVD returns to us is V transpose and not V. Okay, you have to be careful about that. So NumPy's SVD returns V transpose. So the rows of V transpose are the right singular vectors. Okay, so we'll retain the first 2 rows of VT. So that's, once again, this shape is 2 cross 3. So now if you multiply these 3 matrices together, right? So U np dot